Good morning, students. I intended to end physics lesson in this semester, as I told you in my previous video, and start reviewing this week. But since there will be no final examination, we still have enough time to discuss one more chapter in the 11th grade, which is about light wave. And the first part is about the interference of light. Electromagnetic waves, including visible light, are made up of oscillating electric and magnetic fields as shown. The wavelength of electromagnetic radiation determines the color. All visible light has wavelengths between 400 and 700 nanometers. Light exhibits certain behaviors that are characteristics of any wave. Light reflects in the same manner that any wave would reflect. Light refracts in the same manner that any wave would refract. Light diffracts in the same manner that any wave would diffract. Light undergoes interference in the same manner that any wave would interfere. And light exhibits the Doppler effect, just as any wave would exhibit the Doppler effect. In this chapter, the first characteristics of wave that will be discussed is the interference of light. When two light waves from the same source in the same plane are traveling in parallel propagation direction, then the light waves may interfere with each other. There can be constructive interference when the crests of one of the wave coincides with the crest of the other. If the amplitudes of both waves are equal, the resultant amplitude will be doubled. Bear in mind that light intensity varies directly as the square of the amplitude. Thus, if the amplitude is doubled, intensity is quadrupled. If the crests of any wave, of one wave coincide with the troughs of the other wave, the resultant amplitude is decreased or may even be completely cancelled. This is called the destructive interference. We see that the resultant is cancelling each other. The result is a drop in intensity, or in the case of total cancellation, it is blackness. Thomas Young was a physicist who demonstrated interference of light using double slit. To observe interference in light waves, the following two conditions must be met. The first one is the sources must be coherent. They must maintain a constant phase with respect to each other. The second one, the sources must be monochromatic. Monochromatic means that they have a single wavelength. The original experiment used sunlight as a light source, but we will describe the experiment using coherent laser light. Coherent laser light is allowed to illuminate a barrier containing two slits that allow only some of the light to pass through. A screen is placed in the region behind the slits, and a pattern of bright red and dark interference bands become visible on the screen. The bands are called fringes. Constructive interference will produce bright fringe, and destructive interference will produce dark fringe. So there will be bright, dark, bright, and so on. Bright fringes occur when the difference in path delta p is an integral multiple of one wavelength lambda. So if this length is p1, that length is p2, the difference between p1 and p2 will be lambda. So the path difference delta p is lambda, twice lambda, 3 times lambda, and so on. If we want to state in angle, delta theta will be 2 pi, 4 pi, 6 pi, and so on. So for bright fringes, delta p is equal to n lambda, where n is 1, 2, 3, and so on. Or delta theta is equal to 2 pi times n, where n is from 1, 2, 3, and so on. For dark fringes, they occur when the difference in path delta p is an odd multiple of 1/2 of a wavelength, lambda over 2. So if this is P1, this is P2, the difference between P1 and P2 will be n times lambda over 2 n is odd number, or I will just state this: delta p is equal to lambda over 2, 3 lambda over 2, 5 lambda over 2, and so on. Or delta theta is pi, 3 pi, 5 pi, and so on. So for dark fringes, I will just use this: delta p equals n minus a half times lambda, where n is equal to 1, 2, 3, and so on. So you don't have to put in this odd number if you use this equation. Or delta theta is equal to 2 pi multiplied by n minus a half, where n is 1, 2, 3, and so on. So when n is 1, this will be 1 minus a half. A half times 2 lambda is 2 pi is equal to pi. When n is 2, then it will be 2 minus a half. It will be 1.5 multiplied by 2 pi equals 3 pi, and so on. So if you use these equations, you don't have to use that odd number. Now, I want you to look at these analytical methods for fringes. These are the two slits, S1 and S2, and this is the screen. The distance from the slits to the screen is L. And this is the path taken by the light from S1 to the screen. We call that P1. This is the path taken by the light from S2 to the same point on the screen, and that will be P2. And there is a length difference between P1 and P2, which is this part. And if I take a right angle line from this line to that point, I will have this. So this will be a right angle triangle. And if this is theta and the distance between the two slits is d, then I can find that the sine of theta will be this path difference divided by d. So the path difference here will be given by d multiplied by the sine of theta. So the path difference here determines the bright and the dark pattern. Delta p is equal to P1 minus P2. That will be this delta p. And that delta p is equal to d times the sine of theta. So for bright fringes, the difference in path, the path difference, or d times the sine of theta, should be equal to n lambda, where n is 1, 2, 3, and so on. And for dark fringes, the path difference, or d times the sine of theta, should be equal to n minus a half times lambda, as we've seen before, and n starts from 1. So when theta, which is in radian unit, is very small, then I can see here that this is theta, and if this is theta, this angle should be also theta. Then when I write down the sine of theta, it will be equal to the tangent of theta. It will be equal to y over L. Yeah, because theta is very small in radian. So that d times the sine of theta will be equal to d times y over L. So that gives us the equation of bright fringes. D times the sine of theta, or y over L, equals n lambda, and starts from 1. For dark fringes, d times the sine of theta, or d times y over L, equals n minus a half times lambda, and also starts from 1. Yeah. So I will let you see the example problems here. Number 1. Young double slit experiment is done to determine the wavelength of monochromatic light. Some data are gained from the experiment. The distance between the two slits, 0.3 millimeters. It is d, small d, 3 times 10 to the minus 4 meters. The distance from the slits to the screen is 50 centimeters, and that will be L. 50 centimeters, 0.5 meters. The distance from the second dark fringe to the third dark fringe captured is 1 millimeter. I will draw a diagram here for you. If this is the screen, and this is the central bright fringe, And I have here the second dark fringe, which I call Y2. This is the third dark fringe, which I call Y3. It is the distance between them is 1 millimeter. We want to find the wavelength of the monochromatic light. We use this equation for the dark fringes. dy over L equals n minus a half times lambda. Remember what is d? D is the distance between the two slits. L is the distance from the slits to the screen. And this y is the distance from one fringe to the central bright fringe. Yeah, for example, here, if I know the distance from the second dark fringe to the third dark fringe, 1 millimeter, I will say that I have y2, the distance from the second dark fringe to the central bright fringe, and I have y3, the distance from the third dark fringe to the central bright fringe. Yeah, so this y is the distance from a certain fringe to the central bright fringe, and lambda is the wavelength. So now I have y, which is equal to n minus a half times lambda times L over d. So if I want to write down y2, it will be 2 minus a half times lambda L over d. So it is 3 over 2 lambda L over d. Y3 is 3 minus a half times lambda L over d equals 5 over 2 lambda L over d. So the distance from one fringe to the other fringe, which is given 1 millimeter, is y3 minus y2, and that is delta y. So delta y here will be 5 over 2 lambda L over d minus 3 over 2 lambda L over d. So it is equal to lambda L over d. That will be the equation that we can use to find the lambda. Delta y is 10 to the minus 3. Lambda is what we are going to calculate. L is 0.5 here. And that d is 3 times 10 to the minus 4. So I can find that lambda is equal to 6 times 10 to the minus 7 meters, or 600 nanometers. The other problem that I will discuss is from the more problems, number 5. Yeah, this is from your book on page 197. Monochromatic light of wavelength 4000 angstrom is incident on two slits of distance 4 millimeters. The distance from the screen to the slits is 1 meter. So this is d, small d, and this is L. Yeah. Lambda is 4000 angstrom. 1 angstrom is 10 to the power of minus 10 meters. So if we have 4000 angstrom, that will be 4000 times 10 to the minus 10 equals 4 times 10 to the minus 7 meters. We want to find the distance between two adjacent bright fringes captured on the screen, and that will be delta y equals lambda L over d, as we have mentioned before. So lambda is this, L is 1 meter, and that d is 4 millimeter, 4 times 10 to the minus 3. So the result will be 10 to the power of minus 4 meters. B, the distance between two adjacent dark fringes captured on the screen. From dark to dark and from bright to bright, it will have the same equation of delta y. Delta y equals lambda L over d, so it is equal to 4 times 10 to the minus 7 multiplied by 1 over 4 times 10 to the minus 3 equals 10 to the minus 4 meters. And C, the distance from the second dark fringe to the central bright fringe. This is what I call y, y2, from the second dark fringe to the central bright fringe. I want to find y, and the equation is given by n minus a half times lambda L over d, because this is dark fringe. Yeah, I want to find y2, so just substitute n using 2. Then you'll find 3 over 2 lambda L over d. Put in that lambda L over d. So you'll find that y2 equals 1.5 times 10 to the minus 4 meters. And the next question is the distance from the third bright fringe to the central bright fringe. It is y3. The same equation, only that this is for bright fringe. So you have dy over L equals n lambda. Yeah, so the y is n lambda L over d, n lambda L over d. So y3 is 3 times 10 to the minus 4 meters. The distance from the bright fringe to the nearest bright fringe, I guess this is not the nearest bright fringe. This is to the nearest dark fringe. Yeah, so if the distance from the bright fringe to the nearest bright fringe is equal to delta y, then the distance from the bright fringe to the nearest dark fringe is equal to a half delta y. So it will be equal to a half lambda L over d, and you can calculate that the result will be 5 times 10 to the minus 5 meters. That's all, and now you try yourself the more problems on your physics textbook on page 196 to 197, number 1 until number 4. And if you have any questions, you can always contact me. Thank you. I hope this video is useful.